We'll speak about first and second variation of domain functions and application to problems with Robin boundary conditions.
Thank you. First, I would like to thank Henrik Chagolian for the invitation to participate in this program on free boundaries. It's a great pleasure to be here, and I'm also very grateful to the Newton Institute for the facilities they provide for such an excellent working atmosphere. Now, today I would like to report on a project in collaboration with Alfred Wagner from Aachen. We are interested in extremal domains for functionals which depend on the solutions of an elliptic problem in various domains. And one approach is the old method of domain variations, or in a more modern language of shape derivatives. And so let me just explain shortly what's the idea. So we have a domain omega in Rn, and we look at domains which are perturbed domains omega t. And we will assume that omega is smooth, so smooth at least C2 alpha, and also bounded. And omega t will be represented by y equals x plus t times v of x plus t squared over 2 times w of x, and x ranges in omega and t is a small parameter. So t is a small parameter. V and omega and w are smooth vector fields. And in this class of domains, we consider boundary value problems. I just take some model, simple ones. So let's look first at problems of this type. Laplacian u plus g of u equals 0 in omega t. And the normal derivative, so this would be the orthonormal nu t, the normal derivative of u plus alpha u equals 0 on the boundary of d omega. Alpha is a real parameter. Later on we will concentrate on positive values, but for the moment it's just a real number. And with this problem there is energy associated, and this energy is just a Dirichlet integral of u squared omega t minus 2 times the primitive of small g, write it this way, dy plus alpha times now a boundary term which comes from the boundary condition u squared ds. And it is well known, the this problem is a Lagrange, Euler-Lagrange equation corresponding to this energy. And we will be interested in the for which domain this energy is maximal, minimal, if we prescribe, for example, the volume of omega. Or we are also interested, we can also look at integral cost functions, which should be something like this. J of t is a integral over omega t, and some function j of u gradient u x y dy plus some boundary integral. Another type of problem which can be treated by the same methods are eigenvalue problems, like the analogous problem, eigenvalue problem would be in this case Laplacian u plus lambda u equals 0 in omega t, and with boundary Robin boundary conditions. And also in this case, the integral can also be represented by means of an integral, namely the eigenvalues are just the integral over omega t gradient u squared dy plus, now we have a boundary term again, u squared ds divided by the integral over u squared. Omega t. So that's those are some examples we want to discuss, and the goal is to find an estimate for this. Let's take this functional of the form as estimate for E of t, say in terms of for small t. Now the idea is very classical. One can use a Taylor expansion. So by the Taylor expansion, we can write, provided everything is differentiable, E of E of t is equal to E of 0 plus t times the derivative of E of t at 0 plus t squared E second derivative of 0 plus small order terms. So this is called the first variation. And this is the second variation. And we will just focus on those two second variation, domain variation. So this approach is very old. I think one of the first who who made a systematic approach to this method was Adamar in 1907, and then there were several papers by Garabedian and Schiffer, and then there was for sometimes there was not much progress in this direction, but then Simon in 1980 wrote a very nice paper, and by now there are many people working in this field, and you can find pardon?
E. So is U the solution of the problem? Or
Yeah, you're right. U is always a solution of the problem.
do you assume that the problem has a unique solution, or
This will I take it for granted. For the moment, it's just formal. That will be very crucial. Yes. Yeah, and you can find a very collection of references. The very nice book by Henro and Pierre, and also there is also a book by. There are several books, so that's some of the most important contributions. Now the idea is the following: namely to make a change of variables. So it's for the moment I make just everything. It will be formal. It has to, of course, to be checked if this is possible. So we make a change of variables. Namely, for small t, y is a diffeomorphism from omega to omega t. For small t. We can therefore take x as a new variable. So we take x as a new variable. And this has the advantage that we can express those functionals over a fixed domain. And so if we do that, we have to replace dy. This is the area element, and dy is just a Jacobian, the determinant of dy xj of the Jacobian. And if you develop it into a series for small t's, then it is of the form, according to some formulas by Jacobi, 1 plus t times the divergence of v plus t squared. And then we have write maybe the next term I write then divergence of v squared minus the trace of the Jacobian of v squared plus divergence of w plus smaller order terms. Moreover, we have to replace this in the gradient squared of u times times dx. I forgot here to write dx. So this is just du dxi du dxy xy times dxi dys dxj dys times j of t dx. And I will call this just a, this is a aij. Okay, so if we have this, the energy we get for the energy an expression of this type, or maybe before I write the energy, let us just look what comes out. I forgot also the ds. This is equal to some function which depends on t. I will say later more about that, times ds of x. So if we, with this expression, we can just look at a few examples. So if we look at the volume v of t, the volume of omega t, and we are asking for looking for the first variation. This is the integral.
But in the expression of the grade square, you say derivative of u with respect to okay, you are summing in
Over
of the
repeated
same base
indices.
at the end. Okay.
Yes.
Okay.
So if we plug in, we have divergence, just a divergence of omega dx, and this is equal to the integral, the boundary integral v times the normal ds. And the similar expression, the second derivative would be the integral over this term, the second variation of v. And maybe also interesting is the case, let's say the surface of omega t. So if the first variation, this requires a little bit of there is elementary differential geometry. This is the integral over the omega, and then we have the mean curvature of the boundary times v times nu, so the normal, the derivative, the normal component of of v, and the second derivative, this is more complicated. There are not so many places where we have found it, but there is it is contained in the book of Giusti, and it's quite a complicated expression. But there is an interesting special case, namely when we look at we take for omega the ball of radius r, and we take a vector field y, which is volume preserving. This means that the volume of omega t is the same as the volume of BR. Then we can have a very nice expression for the second variation of the surface, namely that's equal to the boundary of the ball of the gradient of the tangential gradient of nu times v squared minus n minus 1 over r squared times nu times v squared ds. And by the isoperimetric inequality, we know that this should be positive because the ball has the smallest surface. So, and this is the case because if we look at this problem, it's this expression here is bigger than the second eigenvalue of the Laplacian on the ball, and we have this condition. This is 0. So the second eigenvalue of the Laplace-Beltrami operator on the ball is n minus 1 over r squared times. So this is really consistent with the fact that the ball is an extremum for the. Oh yeah, yes. No, the W term cancels. It goes the second those because of the volume condition. The W term goes away. If I under this condition, and if the integral over of this is 0, then the W term cancels. This was somehow nice, yeah. So this was also a surprise for us. Okay, so now let's have a look what happens in the case of this W has is needed. Where is the second variation? Yeah, this W is needed in order to have a bigger class of admissible domains perturbations. Without W, we wouldn't have, for example, rotations. So, but it cancels. Okay, so now I'm not going to write you in full details all the expression for the first variation of E, but the E of t, if we use the x variable, it's an integral of over omega Laplacian quadratic form of this type minus 2 times j of u times g of u times j of t dx plus alpha times the integral u square. We have the m of t, this m which comes from the surface, times ds. And now, formally, we just differentiate all those terms with respect to t. And then, if we do that and some partial integration, and using the Gauss theorem on surfaces, one gets a very nice expression for the first variation. Namely E dot 0, and this is something which, if you think about it, it's natural, but first we didn't expect it. Those variations can always be written as boundary integrals. So it's not so important what is going, for example, how the vector fields look like inside, but it's important what happens on the boundary. And V times nu, that's the normal component of the vector field, times now an expression gradient u squared minus 2 times j of u minus 2 alpha squared u squared plus alpha times the mean curvature n minus 1 u squared ds. And now you see the following. If we look at the ball, and if we assume that u is radial, then this whole parenthesis is a constant. It can be, and we have E dot is equal to a constant times this integral. Now under volume preserving perturbation, this is 0. So if we have omega t equals the volume is preserving, then it follows that this is 0, and so the ball is in this case a critical domain. Now if this is consistent with a recent result by Doreen Bucure and collaborators, who have found out that for quite general problems with where G is a power, the ball is really yields a minimum of the energy. But they do it with completely different methods. Now, a very similar result is obtained for the eigenvalue. Then we have here to replace E dot by lambda dot, and here we have 2 lambda times u squared. And so it's the same, provided the eigenfunction is radial. But it's not. It holds also for higher order eigenfunction, not only for the principal one. And we see also from this formula, we see if a domain is critical, then this expression on the bound has to be constant on the boundary. And this yields overdetermined boundary value problem, and as far as we know, I mean, such overdetermined problem have been solved in the case where we don't have alpha for Dirichlet boundary problems by means of Serin's method. Now the second variation. Some words to the second variation, which is a lot of computation, and the difficulty is to find a form, to put it in a form which can be, where some information can be deduced. So first, so the second variation, I also explained it in the case of the energy. Yes, one just derives all those terms twice. And what one gets is something of the which has the following structure. It's a quadratic form in U, which depends also on V and W, minus this integral, G, then the second derivative of the Jacobian determinant, minus a quadratic form in the derivative of U with respect to T, plus something of this type. Yeah. And so this one can, so the idea, the goal is to estimate or to determine the sign of the second variation for volume preserving transformation perturbations. And the problem, the expression which causes a lot of problem is this one. And we have worked from weeks to put it in a form so that we can have some idea what is, how, if we can determine, give some estimate. And it was somehow hopeless to just work with this expression. And then we saw a very nice trick by Simon, Jean Simon. And this trick is, I think it's very clever. Now remember, U was a solution, or is a solution of this in omega T with the boundary conditions. So U depends on Y, on the point Y, and it depends also on the domain T. So if we replace Y by X plus T, V plus, and so on, W plus, then, and we differentiate with respect with respect of t, then we have u dot equals first the derivative with this one, which is a kind.
Did you say before the W was 0?
No. It's not. But it doesn't appear. It doesn't appear in the formula for the first and second variation. We need it in order to have volume preserving. We need it to have volume preserving.
Volume preserving.
And this is volume preserving, but it is not 0. But then it will disappear in the end formula. But it's not 0. No.
But this is for the case of the ball.
No, it will disappear also in general. Yeah, this is not. We need it in order to make sure that so, for example, if you take just a ball and you rotate it, then you have tangent. So V is tangential. Has only tangential components. But this, and you look at the perturbation y equals x plus t v tangential. This perturbation is not volume preserving of the second order. So if you compute the second variation of this, it doesn't. That's why we need a W to make sure that the second order variation is 0 in the case of volume preserving transformations. Okay, so we have this derivative with respect to t plus the derivative gradient u times v plus second order terms or first order terms. And Simon's trick was we should replace u prime by this expression. So if we do that, it's a lot of computation, but this was really crucial that we shouldn't work with the full derivative, but with the domain derivative. Sometimes this one is called domain derivative because we keep the point fixed and derive u with respect to the domain. Then one
U plus t mal u Strich oder u plus u Strich plus u Radius.
this one too.
Ist es U-Punkt von 0 oder ist es?
At 0, yeah. Well, if at 0 we have just like that. And what is nice, because then u prime solves the equation Laplace u prime plus g prime u equals u times u prime equals 0 in omega, and the boundary conditions, normal derivative plus alpha u prime equals some term which depends on u v on the boundary. One can compute it exactly, but I don't think it makes sense that I do it here. Now, what is the strategy to discuss?
If you look look at fluids, what does Simon say?
One is
Between-
with the Euler representation, and one is with the other one. What is
the
it?
Lagrange,
Lagrange. So this is just.
going through Lagrange coordinates.
Yeah, I'm with this moving thing. I'm always a little bit. You.
X is a fixed thing. And Y
So you take u. This is omega t. U t here at the fixed point, and another omega. As delta t. So you and you look at the same point, and you take a look at the limit as ut plus delta t minus ut divided by t at this point, and you don't move the points. Here you moved everything. You move t. You take the derivative with respect to the points and the domain. Yeah. Yes. Okay. So now, what is the strategy to? So, as I said, to discuss the second variations which are of this form, first we replace u dot by u prime. And then u prime solves this problem. It depends on u, which is known, fixed, and this v. And this we can represent the solutions of such an inhomogeneous problem with a corresponding eigenvalue, with an eigenfunction of a Steckhoff type problem. Namely, we look at this Steckhoff type problem equals 0 in omega with the d nu phi plus alpha phi equals mu phi on the boundary. This is an eigenvalue. It's on the boundary. In general, at least, it's called Steckhoff problem. And if under suitable assumptions on G and G prime and U, if this is bounded, regular, there exists a infinite number of eigenfunctions and eigenvalues. And the eigenfunctions can be chosen to be orthogonal in this way. And with this, and they are complete, with this eigenfunction we can represent u prime. Is a sum Ci phi I.
I still have a problem with u prime. U prime is a derivative with respect to x. And in this case, it's
No, with respect to t.
A shape derivative and
Yeah.
dot is a material derivative.
Yeah, right.
okay.
Yeah.
See how
Yeah, material derivatives. That's a correct.
okay. So
Term,
there's
yeah.
only one derivative.
Yeah, only one. Yeah, yes. So we represent this in terms of such and then we can also write V, develop into such a series of eigenfunctions and plug this in and and hopefully this will lead us to something which we can discuss. So this is this program, carried out this program in the case G equals 1. So this is a torsion function, and for omega for balls, for volume preserving transformations, and what comes out is very simple. Namely, the second variation is positive if alpha is bigger than 0. So the ball is somehow a minimum, and it is negative. No, it is really negative if alpha is between 1 over r negative. So in the other, if for small negative alpha, the ball is local maximum. And I think that this you don't have with you. You don't get, you only consider the case where alpha is positive, yeah, because then the situation changes, and if alpha becomes very small, we can have both maximum, minimum. It depends on V, on the transformation. And we have something which further result, namely if we impose a kind of barycenter condition on the perturbation, namely if the integral of x times the normal component of v is 0, then we get an estimate for a better estimate, namely it's a constant which depends on n and alpha, which is strictly positive, times the nu times v squared ds. So in this case we have strict positivity. Here in this case we have strict positivity only for if we don't have translation and rotations. And this gives a more precise estimate. The same type of result can also be obtained for the eigenvalue. The estimates look very similar, and we hope very much to be able to find other examples where one can carry out this program. As I said, the difficulty is that we really we need a lot of information about this, the solution of U in the original domain. And in the case of the linear problems, we have explicit representations of the solution, at least for the ball, and this is certainly a handicap for the whole method, that at least at the moment we still need it. So I hope that during this day we will get some inspiration, and that we will also get some help from some people of you. Thank you for your attention.
Do you have some questions?
So for the eigenvalue with Robin boundary condition in the case where alpha is negative, the conjecture is also that the ball is a maximizer for any alpha. You get also just an interval of values of alpha for which the second derivative is negative?
Yeah, we get the same type of interval for a small interval for small negative alpha. It's a
And it
maximum.
doesn't mean that it is positive for the other value of alpha.
No.
You are not able
For alpha positive, it's
no, alpha negative.
alpha negative. No. I
You
think
don't
it's
know.
not true that it's always for very small alpha. It can be either maximum, minimum, can change. The eigenvalue of a perturbed domain can be smaller or bigger than the eigenvalue of the ball.
Because I thought that the conjecture was true for any negative alpha.
I
You-
don't think so.
so you
I'm
don't
not
think
sure. I'm not sure. At least in this case, I have to check, but I think we can always find perturbations such that which is
could be-
yes.
This would be interesting.
Yeah, that
There
I'm
is
pretty
a
sure.
recent result by Nietzsche Trombetti,
Yes.
where they proved that for every negative alpha,
It's a local
the ball
maximum.
is a local maximum.
I think so. So we have to
Okay, I know for the torsion. The
No.
ball I haven't yet. I had the impression that it should be. But
Another question?
Next question. To calculate the first and second variation, you did change of variable. One couldn't do directly like the Hollenbach formula when the domain is perfect.
yeah, no. I mean, of course, one can derive, but then you get a very, very nasty expression, and somehow you would like to make something out of it, and for that you have to do all kind of clever transformations, because just the straightforward computation doesn't give you much insight. So this is the problem of this method.
You mentioned in especially the first variation that it's because you're using special case of being a ball and canceling things. So after cancellation, you didn't write it down, but you claimed that the ball was the answer, like here. So if you, I got a little bit confused because first you said that you were doing this especially for the ball, and then you get cancellation and much nicer formula.
Yes.
So, and you get that that the energy, the derivative of the energy is zero for the ball. But how do you know that you don't get it zero for other?
Yeah, no, this we don't know.
Oh, okay.
This we don't know, and that's this is over determined boundary.
The reason you didn't write it down.
Yeah, no, we don't know that
I see.
uniqueness, at least not by this method.
Other questions? Let's thank again, Catherine.